everybody. I'm Cambridge Wong from Hong Kong Computer Society, and I am happy to set up this public talk about Alan Turing, the father of computer science, also known as the father of artificial intelligence. And I can see a lot of people from all walks of life, young kids as well as guys like my age. I'm glad to see that. Today's talk, we are very happy that we have Professor Barry Cooper, all the way coming from UK to give this public talk to us. I'm not going to talk about the life of Alan Turing because he's going to talk about it. I just want to do a little bit of promotion. This year is the centenary celebration of the life and work of Alan Turing. And there are a lot of activities happening all over the world. Hong Kong is among one of the places. And in fact, we started quite late. We only started thinking about this in last September. In fact, this event has been organized for 5 years ago by Barry. But things move very fast in Hong Kong, just Hong Kong style. And we are able to already organize quite a number of activities. We have already have some public talks held early this year by me. And May and June will be the peak of the Alan Turing years, because June 23rd will be the 100th birthday of Alan Turing. And just a little bit of promotion. Hong Kong Computer Society is one of the take a lead role in organizing activities in celebrating the Alan Turing years in Hong Kong. With the support of Computer Society, we are able to organize a number of activities that includes a mini exhibition in Hong Kong Art Centers from June 13 to June 30. Okay, hope that you can go there and enjoy the works there. One interesting about the activities in Hong Kong, that the story and the life of Alan Turing not just inspired people in the IT industry, it actually inspired people from all walks of life. We have local artists, we have local writers, all inspired by his story. And in the mini exhibition, you're going to see a lot of works from these artists, like calligraphy, like oil paintings, T-shirt design, a lot of interesting things. And we also have manuscript photos, courtesy of King's College from Cambridge University. And there is also some parties going to held in June to celebrate his 100th birthday, as well as a public talk by me, talk about Alan Turing's wartime effort in breaking the German Enigma code, as well as another talk in November in Chinese University campus, talk about the artificial intelligence. And probably by the end of this year, early next year, we are going to publish a book to record all the Turing's activities in Hong Kong. And I just talked to Professor Cooper. Maybe thinking about an idea that we may compile books that consolidate all the activities happening over the places. Okay, that may be a very meaningful work. So this is a bit of promotion. Let's see. Now, I'm happy to introduce Professor Cooper. He is the professor of mathematical logics from mathematics. Okay, from Leeds University. Okay, his research area is computability theory as well as logic, right? And he is also the chairperson of the Turing Centenary Advisory Committee, as well as the president of the Association Computability in Europe. Quite a complicated name, but anyway, he holds important positions. And Professor is graduate from Jesus College, Oxford University, and he got his PhD from Leicester and Manchester University. So, before I pass the time to Professor Cooper, I mean, one logistic thing, may I ask you to turn your mobile phone to vibration mode or switch it off so that people can focus in Barry's talk. Okay, so without further ado, I pass it on to Professor Cooper.
Well, it's very nice to be in Hong Kong. I almost came in 1996, but for some reason I wasn't. I went directly to Beijing instead of stopping up at Hong Kong. So now at last I made the trip, which is great. I had a short tour this afternoon with Cambridge, and I was really impressed. And it was a beautiful place. As you'll have noticed from the title, I've prepared this under some pressure of time. It's been a very hectic visit to Beijing and now to Hong Kong. I know that this is quite a mixed audience, so you know, if anybody wants to stop me, you know, it's not too big a room, so you know, if you want to ask any questions during the course of the presentation, then that's fine. So I know some people know an awful lot about the technical side, and other people know things about Turing's life and so on. I'm going to be talking very much about the ideas, but the life of Turing will form the backdrop to this, and I'll say things about that as we go through. The kind of emphasis is given by this graphic here. There's the young Turing, 16, a little bit before he did his first great work. And here's the brain, which Turing was always interested in. And he was always interested in how the brain worked and how one built machines that worked like the brain. And so here's, anybody know who this is? I guess people in artificial intelligence will know. Rodney Brooks, who's occupies one of the kind of approaches to artificial intelligence. Of course, as people in the area will know, there are different ideas about how one should approach artificial intelligence, and so Rodney Brooks is one of the kind of more creative people in the area. Right. So Turing lived for a mere 41 years, almost 42 years, and did a fantastic amount in that time, and worked in different areas. People who know him from one area may be surprised to find that he did important work in a different area, but we'll look at the spread of his work during this talk. He went to Sherborne School, which Cambridge's son also went to. And
also Ramsdale.
Sorry?
Ramsdale also.
Oh! So, yeah, in fact, a number of very kind of interesting and remarkable people went to Sherborne School. It was slightly offbeat as an English public school. The reason, of course, why he was sent to Sherborne was because his parents were in India and had a job to do there, and the two boys, their children, were farmed off partly to foster and then later on to Sherborne School. And then this is the end of his life, and this is the house where he lived in Manchester at the end of his life, and this is the statue in Manchester, which has been erected there to commemorate Turing's connection with the city. And there's a plaque on the wall. Now it's not a museum or anything, so if anybody's going to Manchester, they can see the house, but you'll have to talk to the people who live there if you want to see more. I'm told they're very nice people. I haven't actually been in myself. They're very nice people, and I suspect that if too many people go during the Turing year, they might change their mind. But anyway, that's his house. Yeah, right. So what I'm going to do is I'm going to roughly structure the talk around sort of 10 kind of ideas, items of thinking that Turing did during his life. I say 10 big ideas. Some are bigger than others, of course. Some are kind of incredibly important for the history of computer science, and others. Well, I think if you look at, say, the cryptography and Enigma, which we'll visit briefly, that's kind of historically important, but in the history of computing is probably not so much exclusively Turing's contribution. There were lots of people who contributed at Bletchley Park. So, there are different stories attached to each of these items. Right. So what I'm going to so the kind of history of the ideas and also the history of the life and the ideas. Well, what happened in 1936? Well, it suddenly made sense of something that had been with us for some time before. Algorithms, of course, were always important, and you go back to the ancient Greeks and or before. And people always wanted to have recipes for doing things, and so algorithms have always been important in everyday life, and then we get a kind of phase transition in science around the time of Newton and Leibniz, and what happened was that people were doing what they always do, which is trying to describe how the universe works. But Newton raised things to a new level. What he did, he came up with the mathematics that you needed to describe what was happening in nature. And so, of course, people were interested in the motions of the planets and so on, and also the moon, which actually was a problem for Newton. But the planets, they had an idea that the inverse square law played a role. Hooke had the idea, various other people did. But what Newton did, he actually came up with the mathematics that actually enable you to make something of it. And he came up with equations which enabled you to predict how the planets were going to move. And so what you had was mathematics, development of the calculus and so on, and you've got predictions of how the planets moved, and from there on it kind of changed the way scientists, as they became, saw describing the world. What they expected was a little bit more than, this is the way it works. They expected something that enabled them to compute predictions into the future. So scientists started looking for laws of nature which enabled them to computably predict events. And this is what Einstein is referring to. Basically, he's referring to that when we understand a group of natural phenomena, we mean more than we've got something nice, to help us understand it. We mean that we've actually found a constructive theory which embraces them. So we've got something that actually helps us tell what's going to happen, and in that way understand things rather more deeply. So that's the way scientists work. Now, it's said that this is sometimes underlying. This is sometimes called the Laplacian model of the universe. That it's the idea being that if the scientist has enough information and has the right laws, they can tell what happens in the universe at any future time. But it's not really a model until 1936. 1936, we have a paper by Alan Turing, which it was designed to solve a problem of Hilbert. It was David Hilbert had this idea that basically you could solve any problem, And in particular, he had this idea that you could solve the problem of validity of statements in logic. And it's called the Entscheidungs problem, of course, and Entscheidungs decision problem. And Turing got interested in this problem, and to show that you couldn't actually do this, you couldn't actually find a decision process, you had to have some description of what it meant to have a computation. So if you wanted to show that something wasn't computable, you had to know what computability was. So he came up with a model, and this is it. And there's something kind of amazing about this model, which is that it's as simple as anything. It's abstract. It's not a real machine. It's a kind of an abstraction, but it's incredibly simple. So the hardware is trivial. In fact, it's non-existent because it's abstract. But you know, even if you embody this machine, it's still going to be a pretty trivial piece of machine. Well, I should say that of course the engineers will disagree, because even this is hard to materialise as people found out in the early days of the computer. But to the mathematician, trivial hardware. Action's simple. I mean, all the machines. I'm assuming there are some people who haven't seen what a Turing machine is. I'm sure that a lot of people have. But the idea was that okay, computation is all about doing something with information. You start off with some information, you do precisely define things to it, and you end up with some other information that you've morphed it into. So you take a tape, and you want things tidy, so you divide it into bits and I should say cells, and you write things in the cells, and usually you keep to binary notation, so you have to say zeros and ones, and zeros can be interpreted as blank if you want. So you've got a tape like this. You assume that, because you're doing mathematics, you assume that your tape is as big as you're ever going to need, and so we don't say you've got an infinite tape. That's kind of annoying the people in the real world too much. But you say you've got an infinitely extendable tape, so you can make it as long as you like. You can get as much memory as you want. And then you've got to do something to the tape, so you have a reading head that can read, that's aware, that can tell what's on the tape, and you've got to have some way of structuring what the machine does, and different models of computation have different ways of structuring. Well, of course, Turing was interested in the brain, and so he thought in terms of a human computer at that time. And a human computer was a person who followed instructions. So a human computer would be given, told what to do, and they wouldn't think that they wouldn't think intelligent thoughts. They just carry out what they were told to do, and that's the program. But the internal state was modelled on states of mind. So Turing was, thinking, well, I'm building a brain, as he said later on. These are states of mind, and they kind of structure what we do. So, for in different states of mind, we do different things, and that's. So you get a program, and it's made out of simple instructions. And of course, if you're a computer scientist, you have a particular way of writing these instructions. I'll on the next slide, just say that hardware trivial, actions very simple. The actions would be move one square to the right, one square to the left, or change the symbol, either erase or print. So that's really all the machine does. Very simple operations. But of course, the fantastic thing is that you can with a little bit of work, you can actually show that anything computable can be computed by such a simple machine. Now, why do we believe that? Well, of course, over the years, lots of other models have been invented, and there are a couple of models that predate this one, which is recursive functions and lambda computability, and they were shown to be equivalent. Turing did some of this work showing equivalence of models. And the experience, it's kind of like, there's no real proof of this, of course, because this is what you can compute is an intuitive notion unless you attach it to a model, and the attaching of the intuitive notion to precise ones is something that seems to hold up. Right. So you can compute anything, which is amazing. It looks, of course, anybody who's programmed a Turing machine will know that it is rather amazing, because it's really quite hard to get it to do anything interesting, without some kind of inductive process of building up more and more complicated programs. So it can compute anything, it turns out, and anything that you can do via a reasonable model. And here's the kind of the important thing: the computing power lies in the program. So unlike machines of the past, you didn't have to build a new machine every time you wanted to compute something different. What you did is you just wrote a different program, which brings us into the future. And here's one way of describing elements of the program. You have a statement like this, which says, if I'm in internal state I, reading a symbol, then what I do, if that applies, then I carry out elementary action, right, left, print, erase, and go into a new internal state. And what you have, a program is just a collection of these kind of instructions, and then you apply, what you do is you have some conventions. You compute on numbers by inputting numbers as sequences of ones, say, and you decide you're always going to start off in state Q0, reading the leftmost one, and you compute away using the program. And what happens? Well, if the machine keeps on going, then you don't know whether it's going to stop or not. You just carry on computing. If you never stop, then you don't get a computation. But if you do, if you reach a stage where no one of these statements applies, then you just count up the ones on the tape, and you're finished. That's your output, the number of ones. So that's the disembodied computing machine. Now, of course, people have noticed there's actually a kind of there's a kind of faultiness of the mathematician's way of looking at things, in that if you want to do anything with such a machine, you do actually have to build it. And people whose job it is to build computers know that the universal Turing machine has a little bit more to the story than that simple picture. So there's all these cartoons that and so on that you see over the years. So here's a joke about Turing solves the halting problem only to discover that the real problem with his machine is what to do with all the tape. And here's a nice kind of Heath Robinson type of embodiment of the Turing machine. It's got if it's going to have to compute, then you do have to have some mechanisms. Here's somebody's built a Lego Turing machine. There's some nice animations, of course, as people will know. Here's on YouTube and so on. Here's a nice one. In Beijing, they had John Hopcroft giving a talk, and he of course has written an important book with Hopcroft and Ullman. It's a standard book on automata and so on. I expect lots of people know this book. And here's this. Here's your Turing machine. It's embodied. It's got eyes and it's doing stuff. It's got a brush here to print and erase and so on. And it's looking a bit discombobulated because this woman's saying, as Hopcroft and Ullman point out, we can define U formally as a 7-tuple, such like that. The machine is kind of not convinced about this. So of course, if you're a computer scientist, then you don't have quadruples, you have septuples. And there's a nice. This is my favourite. This is my favourite embodiment of the Turing machine. There's an imaginative cartoonist called Jin Wicked, lives in Houston in Texas, and she's embodied Turing himself as a Turing machine, and there's some kind of sense to this in that it's called the universal Turing machine, I think she calls this, there's some sense to this, because if you read David Levitt's biography of Turing, then he comes up with this idea that actually Turing did identify with his machines, and this is, in a sense, this kind of constructive way of thinking that he had. It really rather fits this picture. Okay. Now, a lot of people know about the Turing machine. A lot of people they probably think, well, I could have done that. Well, there was a kind of a really key idea, which a lot of people know, of course, which is that the really kind of smart thing that Turing did in this paper was he came up with a Turing machine which could compute like any other Turing machine. And so he came up with a universal machine. Now, the way it simulated other Turing machines, there was kind of a slight trick to this. There were various tricks, of course. There was the idea of coding machines. So a program is just a collection of quadruples. Well, you could code that up using powers of prime numbers and things like that if you wanted. And you could get a list of all the possible programs. And of course, the list of all the possible programs was a list of all the possible Turing machines, because a Turing machine is basically just its program. And so you could have the ETH Turing program, and then you could define a function which it computed. Now, of course, given the right conventions, you could use your ETH Turing machine to compute functions of any number of places. So you could you just use a conventional way of inputting a k-tuple, and then you could set your program off on this k-tuple, and it would give you an output maybe, and that would the result. So the result you could notate like this. So k gives you the number of places, e gives you the place in the list of the list of Turing machines, and this is the function notated. And did he know it all already, or or did I lose him? Okay, right. So that's the notation, and the way that the universal machine works is you've got some Turing machine U for universal Turing machine, and what you do is you give it a pair, and what it does, you've decided that it's going to be a pair that you're going to compute on, and what's this? This is going to be the the number of the ETH Turing machine, and this is going to be the number that you want to compute on. And so this universal machine has the property that it computes exactly like the ETH Turing machine on that input. So there's your universal machine. Now that is essentially what a stored program computer does. Except of course that when you compute, you don't feed in your program and what you want to compute on. You install the software, but it's installed as data in the same way as the thing you can compute on is, and you compute away, and your laptop is a universal Turing machine essentially. So this is an anticipation of the stored program computer. Stored program because there's the E, which you input, and your Turing machine stores it while it's computing. Right. So this is something that now, of course, Alan Turing went to Princeton in the late 1930s, and of course, as you know, there are all sorts of famous people who were in Princeton at that time. Or shall I say that there are all sorts of famous people who were attached to Princeton at that time. People like Gödel actually wasn't there. He was attached to Princeton, but he wasn't actually there when Turing went, much to Turing's disappointment. And one or two other people he wanted to meet weren't there either. But von Neumann he did meet, and von Neumann did see Turing's 1936 paper, and it said that by 1938 anyway, John von Neumann did know about this paper, and he immediately had digested the idea of the universal Turing machine, the stored program computer that was related to that, and he of course wrote a famous report in 1940s, in which he described the von Neumann architecture for that was had a big impact on the history of the computer. It was embodied in all sorts of early versions of the computer, and I think at the time he didn't say that he'd got much out of Turing, but later on he did acknowledge it later on in his Higson Symposium lectures in around 1948. Now, I say that it's the programmer's data which is the essential idea here. So there's von Neumann, and that's his report, and that's the effect that he had on the history of the computing. Of course, the people that had the most influence on were people in Philadelphia. A lot of funding went into the American early computers, and of course von Neumann played roles in other important developments. Right. Now, what was happening here? Well, what you had was basically a new computing paradigm. You had this idea of omnipotence. You had this idea that you could compute anything using this universal machine. And of course, as one does when one has a new idea, one gets a little optimistic, and one thinks, fantastic, I can compute anything, I'll compute what a brain can do. And so we had the idea of the omnipotent computer, and here's Turing. He was quoted as saying, I am building a brain during the 1930s when he was trying to build his prototype. Now, I don't know, functionalism, AI, there's a lot been built on this paradigm, and the philosophers, of course, have applied the paradigm to the brain, as Turing did, and there's a philosophical idea that the universality can be stretched to enable you to simulate any machine on a Turing. On a universal Turing machine. And so the idea is that you can take different computing platforms which embody a universal Turing machine, and you'll be able to simulate on that platform another computer if you like, and if you like you can take this idea into the theory of mind and think of yourself embodying the human mind on a suitably constructed computer. And then, of course, in computer science, you have this idea. You have this idea of the virtual machine, and you can, and this is kind of embodied in various guises, Java and Unix and so on. This is Hilary Putnam, of course, who wrote this very influential article back in 1960. And this has been, people have taken this to extremes. His